Sound waves can be heard, but not seen. Waves of sound are generated by something vibrating the air. A vibrating object sets the air next to it into motion, compressing and expanding its density with each vibration. That's why a generated sound wave carries the same frequency as its source. The force that drives a sound wave is due to the change in pressure as the density of air increases or decreases.
Just as the speed of water waves depends on gravity, the speed of sound depends on the pressure and density of air. In air, the speed of sound is approximately equal to the square root of the pressure divided by the density of the air.
Around the world, in the most gentle setting or the most violent, countless bits of matter vibrate in unison. And according to the principles of harmonic motion, they create the phenomenon of the mechanical wave.
And so, now we're in a position to understand why Isaac Newton was playing with a pendulum in a corridor at Trinity College. He had worked out his theory of the speed of sound and decided that it ought to be equal to the square root of the pressure of the atmosphere divided by the density of air. And when he put in those values to find out how big it should be, the result was 979 English feet per second. Newton was trying to measure the speed in order to test his theory to see if it was right. Now, as I told you, Newton's measurement was not the very best of the time. The best was made by a man named William Durham, who got a result of 1,142 feet per second. Now, at this point, Newton had to do what every scientist must do all the time. He had to make a value judgment. His theory predicted this number. The experiment measured this result, and the question is that good or bad? Is the agreement or disagreement between these two numbers satisfactory or unsatisfactory? Now, we know, in retrospect, looking back, that what Newton had done was an absolutely stunning intellectual accomplishment. Because before Newton, nobody had the foggiest notion of what the speed of sound should be. Newton came along, had the right idea of what sound was, and calculated a speed that was correct to within 20%. And so he should have been satisfied. Newton considered this situation, and he found it totally, completely unacceptable. The reason was because the entire thrust of the scientific revolution from the time of Copernicus on was to cast magic and the occult out of science. Newton had introduced into science his theory of gravitation, in which invisible forces acted between bodies at vast distances with nothing in between. And that smelled to Newton and his contemporaries like magic. Newton's defense of his own theory of gravity was it had to be right because it worked so well. That is to say, it gave precisely correct numerical predictions. And that, he said, is the true test of the correctness of a scientific idea. But if precise agreement is the true test of his theory of gravity, it had to be also the true test of his theory of the speed of sound. And the speed of sound was wrong by 20%. And so Newton set out to make his theory correct. What he did has a special name in science. It's called fudging, and it's something that no scientist ever does. And this is no ordinary fudging. This is fudging by the great Sir Isaac Newton in the ultimate classic of science, the Principia itself. I'm going to tell you what he did. Listen carefully. The first thing he said was, look, sound travels 979 feet each second not through the air, but through the space between the molecules of the air. It actually goes a larger distance. It goes further in each second because the molecules themselves take up some space. How much space do the molecules take up? Well, he said we know that the density of air is 470 times less than the density of water. In other words, if we imagine a volume like this containing air, all of that air could be condensed down into 1/470th of that volume, a little thing like that. And if we did that, the linear distance that it took up would be 1/9 of the original linear distance. So the extra distance that the sound travels in 1 second is 979 divided by 9, which is an extra 108. And if he adds that to this, we get 1,088 feet per second. Well, that's a little closer, but it's not good enough for Newton. And so he says, well, look, air is 10% water vapor. How does he know that? He doesn't say. And of course, the water doesn't participate in this process. Why not? He doesn't bother to tell us. But he says, when we divided by the square root of the density of air, we made a mistake. We should have divided by the square root of 9/10 of the density, because the other 10th is water. So we must add to this number 1,088 divided by the square root of 0.9. That's about an additional 5%, about 55 feet. And so if he adds 55 to this, he gets a result of 1,143 feet per second, compared to the measurement of 1,142 feet per second, and now Newton was satisfied. And that's the way the great Sir Isaac Newton made science and reason triumph over magic and the occult. I'll see you next time.
The real reason for the discrepancy between Newton's calculation and the measured speed of sound is that air is heated when it's compressed, causing it to spring back slightly faster than expected. The effect is so subtle, it would not be discovered until a century after Newton's death.
Funding for this program was provided by the Annenberg CPB project.
You can take a video course for credit, or teach one. You can buy these programs on video cassette, and our print and audio materials. You can join in our workshops, or learn more about math and science education reform. Talk to us. The Annenberg CPB Projects. www.learner.org. 1-800-LEARNER.